Okay, welcome back. This is Unit 6 Recording 2, and in this recording, the first type that we're going to work on are single replacement reactions. And this general formula works for all the different types of chemical reactions. You'll want to write the charges or the reactants, and then pair elements of opposite charge in the products, checking for any diatomic elements, and then cross the charges to charge balance the new products. And then you're going to use coefficients to balance the equation. So we're going to do several examples here and walk you through it. So the first one here we have is calcium reacting with sodium phosphate. And as I said in the previous slide, we're going to assume that all these reactions take place. They may not actually take place. The order of the metals might be such that the reaction is no reaction, but to get good practice here, we're going to assume that all of them take place. So the first step here is to write the charges. Calcium is a +2 charge, sodium is a +1 charge, and phosphate is a -3 charge. You might ask me, well, how do you know that? Well, calcium is in group 2, so all the elements in group 2 tend to lose 2 electrons to become positively 2 charged. Sodium is in group 1, and so they lose 1 electron to become positively 1 charged. I always tell students to write those charges above the groups on the periodic table so that they will have that as a guide. Phosphate is a polyatomic ion, and you'll just need to memorize the charges of those polyatomic ions. So now we are going to write the elements of opposite charge on the product side. So calcium is +2 and phosphate is -3. And then sodium will go by itself. We don't need to write sodium's charge because it's not combining with anything else. And so we will crisscross the charges so that we will have a charge balanced compound. So we have a 2 here and a 3 here. So we'll need 3 calcium atoms for every 2 phosphate polyatomic ions. And now what we'll need to do is go through and balance the reaction. And most reactions you can just balance by inspection. And what I recommend is you start on the left-hand side and work your way to the yield sign and then go back and recheck. So here we have calcium, or just have 1 calcium atom here, but we have 3 on the product side, so we're going to put a 3 next to the calcium. So now calcium is balanced. Working towards the yield sign, we're going to balance sodium. We have 3 sodium atoms on the reactant side, but we only have 1 on the product side, so we'll put a coefficient of 3 next to sodium. So that will be balanced for sodium now. And now we have phosphate. We have just 1 phosphate polyatomic ion on the reactant side, but we have 2 on the product side, so we'll put a 2 here. Now, we've balanced 1 time to the yield sign, and now we need to go back through and double check to make sure everything is still balanced and adjust accordingly. 3 calciums, so we're good there. 2 times 3 is 6 sodiums, but we only have 3 sodiums on the product side, so we're going to have to change this to a 6. And now we have 2 phosphates and 2 phosphates, so now we are balanced. Okay, take some practice to do these. And the main thing to do is when you're balancing equations, just take them one at a time. Balance everything through 1 time first and then go back and double check. Don't balance 2 things and panic and not get that 3rd one because a lot of times you'll just keep rolling up numbers and never getting there. So always balance everything through 1 time first. Don't look back at what you changed when you do that and then go back through and change it. I think you'll be happy with that. Okay, let's do another one. All right, in this one we have iodide and strontium perchlorate reacting. So iodide is a -1. Strontium here is going to be 2. Perchlorate's -1. -1 times 2 gives me -2. So strontium will have to be +2. And here, this one's a little weird because we have a nonmetal replacing another nonmetal. And so these guys are going to replace each other. So strontium will dance with iodide, and then we will have perchlorate by itself. Okay. So strontium is +2, iodide's -1. Of course, we've got -1 over here. And then we just crisscross the charge. We'll put a 2 down here next to the iodide, and now we have a charged balanced strontium iodide. So now we got to go through and double check and balance. So we got 2 iodides on the reactant side, and we have 2 iodides on the product side. We have 1 strontium on the reactant side, 1 strontium on the product side, so we're good there. 2 perchlorates, but we just have 1 here. So if we put a 2 next to perchlorate, we're balanced. So let's double check. 2 iodides, 2 iodides. 1 strontium, 1 strontium, 2 perchlorates, and 2 perchlorates. So now we are balanced. All right, continuing on. We have aluminum iodide and oxygen reacting here. Aluminum is +3 because it's in group 13, right? Iodide is -1 because it's in group 17. Oxygen is always a -2. It's in that group, I think it's 16, that's the -2. And so now aluminum is going to dance with oxygen because they have opposite charges. Put your charges back over the top. And then we have iodide. And iodide is one of the 7 diatomic elements, so it will be I2. All right, so now we have to crisscross the charges on the product side to get a charge balance reaction. We have a 2 here and a 3 here. And now we'll go through and balance. So 2 aluminum, 2 aluminum. Well, 1 aluminum on this side and 2 there, so we'll have to put 2 there. 2 times 3 is 6 iodides. So 3 times 2 is 6 iodides. Oxygen is 3 here and 2 here. So what is a common multiple of 3 and 2? Well, 6, right? So we'll have to put a 2, or a 3, excuse me, next to the oxygen and a 2 next to the aluminum oxide. So now we have 6 atoms of oxygen on either side, and we'll have to go back through and recheck. So 2 aluminum, 2 times 2 is 4 aluminum here, so we'll have to change aluminum to 4 here. 4 times 3 is 12 iodide. We got 3 times 2 is 6, so we're going to have to change this to a 6. This one's a little harder, right? And now 3 times 2 is 6 oxygens, 2 times 3 is 6 oxygens there, and I think we're balanced, but let's go back through and double check to make sure. 4 aluminum, 4 aluminums, 2 times 2 is 4. 4 times 3 is 12 iodides, 6 times 2 is 12 iodides, and 3 times 2 is 6 oxygens, 2 times 3 is 6 oxygens there. So now we are balanced. That one was a tough one. All right, so let's hope this one's a little easier. But let's see, we got magnesium, which is +2 in group 2, bromine, -1, cesium. Okay, so cesium is -1. Always have your periodic table next to you guys. All right, so now let's see what we can do with the products here. So magnesium is going to dance with cesium. Excuse me, cesium is +1. So magnesium is going to be by itself, and cesium, since it's +1, is going to dance with bromine, which is -1. So there we go, and then we will balance. So magnesium is balanced because there's only 1 atom of each. Bromine, there's 2 atoms of bromine on the reactant side and 1 on the product side, so we'll have to put a 2 there, and then we'll have to put a 2 by cesium to get it to balance. So let's double check. 1 magnesium, 1 magnesium, 2 bromines, 2 bromines, 2 cesiums, and 2 cesiums. So we're balanced there. Notice here, you might have thought, well, shouldn't cesium bromide go first? It doesn't really matter which product goes first, just as long as you have the right products represented. All right, so now we have potassium sulfate and aluminum. So potassium is +1, sulfate's -2. It's one of those polyatomic ions that you have to have memorized. Aluminum is +3, and so now potassium is going to be by itself, and aluminum and sulfate are going to dance because they are opposite charged. So it's always positive by negative. Potassium is not one of the 7 diatomic elements, so we don't have to do anything there. And so now we have to charge balance our products. So we will put a parentheses around the sulfate. There's 3 sulfates and 2 aluminums. And so now we have a charge balance compound. If we forgot to put the parentheses, then we would really mess up the ratio of atoms. We'd have SO43, and that would be awful. So we have those polyatomic ions. If you have more than one of them, put parentheses around them and crisscross the charges. So now let's balance. We have 2 potassiums on the reactant side, so we'd have to put a 2 next to potassium there. We have 3 sulfates, so now we have 3 sulfates. Now it might be tempting to go back and rebalance potassium, but remember what I said, always go through and balance everything one time first and then go back and change or readjust. So here we have 1 aluminum, we'll put we have 2 aluminums on the reactant side, 1 aluminum on the, 2 aluminum on the product side, and 2 aluminum on the reactant side now. So now we're going to go back through and adjust. We got 3 times 2 is 6, so we're going to have to change our coefficient here to 6. 3 sulfates, 2 aluminum, and 2 aluminum. So now we're balanced. Now, sometimes on exams and standardized exams and exams that somebody else might give you, they'll ask for the sum of the coefficients of the balanced equation. So here we'll have to be very careful, because if there's nothing here in front, the coefficient is assumed to be 1, and you might forget to count that when you're adding them up. So the sum of the coefficients in this reaction is 3 plus 2 would give you 5, plus 1 would give you 6, and 6 would be 12. So the sum of the coefficients here would be 12. So if we have another example here. Oh, we have some single reactants. Sometimes you'll be asked to balance a composition reaction, like this one, aluminum plus oxygen. So you just write the reaction in metal by nonmetal form, do the charges like before, and crisscross the charges, and balance. So here we would have a 2 in front of the aluminum, and oxygen, we have a 2 and a 3. A common multiple there is 6. So we'll make the oxygen on the reactant side 3 times 2 is 6, and then 2 times 3 is 6 on the product side. Now we'll go back and double check. We'll have to change our aluminum because now we have 4 aluminums on the product side, and so we'll put a 4 here, and we are balanced. Let's do another one of those. Magnesium and phosphorus reacting together. Magnesium is +2, phosphorus is -3. So we have Mgp +2 minus 3. So we've got a 3 here and a 2 here. 3 and 2. And I believe that balances that one. That one's nice because it was easy to balance. So 3 magnesiums, 2 phosphorus, and 2 phosphorus. So in the next slide, we will do double replacement reactions, predicting products and balancing, and the same steps apply. Okay, so now we have double replacement reaction, and the steps are the same. So let's go through those and do some example problems. So here we have potassium oxalate. This is an interesting one because it is one where you probably don't have oxalate on your list. At least I did not include it in mine, but it's a pretty common polyatomic ion, and you might want to add it to your list. It is -2 charged. titanium hypochlorite. Hypochlorite's -1. Titanium is in the transitional group. So to find the charge, you have to look at the nonmetal side. So -1 times 3 gives us -3. So this side, you just have one of those titanium atoms. So this one has to be +3 for it to be a charge neutral compound. Those are a little more difficult, but you just got to remember that if you have the symbols of the compound, you can figure out the charge. So now we're at the high school dance, and potassium's dancing with Miss Dichromate, and titanium is dancing with hypochlorite. So they are friends in this group of dancers, and so they change place. And so potassium wants to learn the dance that titanium is teaching Miss Hypochlorite. So he goes over and dances with hypochlorite, and titanium dances with oxalate. So they switch dance partners, always positive by negative. So potassium will dance with hypochlorite, and then titanium will dance with dichromate. Why? Because it's so much fun. Okay, so now that we've got things of opposite charge paired, we'll write the charges back over the top, and we'll cross those charges. If they have the same charge, you don't have to cross them, right? Because that's a 1-to-1 ratio. But they have opposite charges or different charges. Titanium was +3 here. Dichromate was -2. Put a 2 here and a 3 there. So now we are going to put our coefficients to balance this equation. This is called a skeleton equation, one that's not balanced. So we'll start on the left-hand side. We'll work to the arrow or the yield sign, and then we'll go back and double check. Balance everything through one time first, and then double check. Okay, so we got 2 potassiums here. So we'll need the coefficient of 2 in front of the hypochlorite. We got 1 dichromate here and 3 dichromates on the product side. So we'll have to write a 3 here. Now it might be tempting to go back and to change potassium, but like I said, don't do that. Balance everything through one time first and then go back and double check. Got 1 titanium here, we got 2 here. So we're going to put a 2 in front of the titanium. We got 2 times 3 is 6 hypochlorites, but notice here we only have 1 hypochlorite, so we're going to change this one to a 6. Okay. So now we've balanced to the yield sign. We'll go back and check. 3 times 2 is 6. 6 potassiums on the product side also now. 3 oxalates. 3 oxalates here. 2 titaniums. 2 titaniums. 2 times 3 is 6 hypochlorites and 6 hypochlorites. So now we have a balanced equation. Yay! All right, let's go on and do another one. 5, because they're so much fun. +2 for magnesium. -3 for phosphate. Always write the charges first. +1 for sodium. -1 for chlorine. So now we have magnesium dancing with chlorine. Always opposites attract in chemical reactions. And then sodium and phosphate. Sodium's +1. Phosphate's -3. Okay. So now do not forget to charge balance your products. A lot of times people get anxious and they'll try to balance the equation and then they'll have trouble balancing it, and the reason why is they didn't charge balance their products. Even if you do that and you go back and you find you're having a hard time balancing it, maybe you didn't cross a product right or looked up a charge wrong. So always double check that if you're having trouble balancing the equation. So here we have 3 magnesiums. We only have 1 magnesium on the product side, so we'll use the coefficient of 3 to get that one to balance. We have 2 phosphates. We only have one. Ooh, what did I forget to do? I forgot to cross them, see? Just like I told you. So you have to cross those. And I noticed it right away, so hopefully that won't screw us up. If it does, we'll just go and change them, right? So 3 magnesiums, that didn't change that. It will change the chlorine. 2 phosphates, and we have only 1 phosphate on this side, so let's write a 2 here. 1 sodium, 2 times 3 is 6 sodium, so we'll put a 6 here. And 6 chlorines, and we have 3 times 2 is 6 there. So let's double check ourselves and make sure that we're balanced. 3 magnesiums, 2 phosphates, 6 sodiums. 2 times 3 is 6 sodiums, 6 chlorines. 3 times 2 is 6 chlorines. So now we're balanced there. Okay, let's go on to the next one. Plus 3 minus 2 plus 2 minus 1. ALI plus 3 minus 1 plus MgSO4 plus 2 minus 2. Okay, so let's don't get in a hurry this time. Let's charge balance our compound before we try to balance it. Put a 3 here, right, because you got 3 and a 1. You got a 2 and a 2, and so you don't need to crisscross those because that's a 1-to-1 ratio. And so now we are ready to balance. 2 aluminums on the reactant side, so we'll put a 2 in front of the aluminum on the product side, so that will balance. We have 3 sodiums, so we'll need to put a 3 sulfates. We have 3 sulfates, and we have 3 sulfates on the product side. We have 3 magnesiums on the product side, but we only have 1 on the reactant side, so we'll have to put a 3 there. 3 times 2 is 6, and 2 times 3 is 6. So let's double check ourselves and make sure that we are balanced. 2 aluminums, 3 sulfates, right? 3 sulfates, 3 magnesiums, and 3 magnesiums. 3 times 2 is 6 iodide atoms. 2 times 3 is 6 iodide atoms there. So we're cool, we're balanced. All right, so this next double replacement reaction has transitional metals in it. So we'll have to use the non-metal side to figure out the charge of the transitional metal. So in this case, dichromate's minus 2. So this side, or the non-metal part of the compound, is minus 4. So the metal side's got to be positive 4. So it's going to have a copper 4 dichromate. Nickel is another transitional metal. We have a -1 for perchlorate. -1 times 2 gives us -2. So this side's got to be positive 2. And so now we are going to have to pair things of opposite charges. So copper is going to dance with perchlorate, and nickel is going to dance with dichromate. Dichromate di. Okay? And so we have to put the charges back over the top. Just transfer them from the other side. +4 minus 1 plus 2 minus 2. And so now we need to charge balance our products. Make sure that they're written correctly. So 4 coppers need to have 4 perchlorates to balance it out. Nickel's +2 and dichromate's -2, so it is balanced. And so now we just got to go through and balance our equation. So we have 1 copper and 1 copper here, 2 dichromates, but we only have 1 dichromate on the product side. So we'll have to put a 2 there. 1 nickel, but we have 2 nickels. So we have to put a 2 there. 2 times 2 is 4 perchlorates. And so we have 4 perchlorates on the product side. So we are balanced. So I'm going to ask you a question. It's tricky here. We need to go back and double check first. Let's do that. 1 copper, 2 dichromates, 2 dichromates, 2 nickels, 2 nickels. 2 times 2 is 4 perchlorates, and we have a 4 there, so it's balanced. So what is the sum of the coefficients in this balanced equation? All right, give you a minute to think about that. Okay, so let's figure it out. The tricky part here is to remember that if there's nothing there, it's assumed to be 1. So 1 plus 2 is 3, and on the product side, 1 plus 2 is 3, so 3 and 3 makes 6. All right, so I'm going to ask you, what is the sum of the coefficients of the products? The products on the right-hand side, so it would be 3. What are the sum of the coefficients of the reactants? So that would be 3 also. So be thinking about those types of things as we go along. This next one's a little unusual in the fact that we have a polyatomic ion that's positively charged. Ammonium is +1 and nitrate's -1. +1, -1. So this one would be NH4CN, ammonium cyanide, plus sodium nitrate. +1, -1, +1, -1. So this one's really easy because it is balanced as it is written. So the sum of the coefficients here would be 4, right? Because you have 2 reactants and 2 products. Hey, all right, so now we are going to learn how to balance the 5th type of reaction, which is a combustion reaction. And these are a little bit more difficult to balance unless you know some tricks. And I'm going to teach you all the tricks to balancing these. So you'll be an expert here in a minute. Combustion reactions. All right, so these are a little different. You actually kind of balance them the same way, but there's one little trick at the very end that will help you to balance them. So you balance carbon and hydrogen first. Of course, those are on the reactant side. So you'll start on the left-hand side and work to the yield sign. So balance carbon and hydrogen first, and then oxygen last. If there's an odd number of oxygen atoms, you'll make a fraction to balance the oxygen. And then you multiply through by 2 to get that fraction taken care of. And so let's do some examples. These instructions don't mean a lot without the examples. So let's start with C8H18 plus O2. So if we have excess oxygen, the products will always be carbon dioxide and water. And in these types of reactions, you don't need to put charges above the symbols and crisscross them. You just kind of have to have the products memorized. So if you have a hydrocarbon, carbon and hydrogen combined with oxygen, you know you're either going to have carbon dioxide in water or carbon monoxide in water. This first one is carbon dioxide. And then the second one, you have limited oxygen, and so you're going to have carbon monoxide in water. And so let's balance those. See if we got our pen here. Okay, let's get our pen. So it'll be CO2 plus H2O. So we're going to balance carbon and hydrogen first. So we have 8 carbons here, so we'll put an 8 in front of the carbon on the product side. We have 18 hydrogens, so 2 times 9 will give you 18. So now we are balanced for carbon and hydrogen, and now we'll do oxygen. So let's add up our oxygen. It's a little tricky because you have oxygen and carbon dioxide, and you have oxygen and water, so you have to keep that in mind. 8 times 2 is 16. 8 times 2 is 16. 9 times 1 is 9. And 16 and 9 make 25. Okay. So we have an odd number of oxygen atoms. So now what we're going to do is we are going to make a fraction. So we'll put 25 over 2. Well, you have to have whole numbers when you balance chemical reactions. And so now to get rid of this 25 over 2, we're going to multiply everything through by 2, and we should be balanced. So remember, there's nothing there, so it's assumed to be 1. So 2 times 1 is 2. 2 times 25 over 2 gives us 25. 2 times 8 will give us 16. And 2 times 9 will give us 18. All right, so we're balanced. So I've done this enough to know it is balanced, but I'm going to prove it to you by re-examining the equation and adding up. So 2 times 8 is 16, 16 carbons. 2 times 18 is 36. 18 times 2 is 36 hydrogens. 25 times 2 is 50 oxygens. 16 times 2 will give us 32. And 18 and 32 gives us 50. Carry the 1. Okay. So we are balanced. All right. So let's do the limiting one. So we know our products will be carbon monoxide. Carbon monoxide makes us moan. And H2O. So, like before, we'll balance carbon and hydrogen first. 8 and 18. All right, 9 times 2 will give us 18. And so now we got to work on our oxygen. So 8 and 9 makes 8 and 8 is 16, and 1 makes 17, correct? All right. So now we'll do 17 over 2 and multiply through by 2. 2, 17, 2 times 8 is 16, and 2 times 9 is 18. So now we have 2 times 8 is 16, 16. 2 times 9 is 18, just like before. But this time, since we have carbon monoxide, it's just going to be 16 and 18. Makes 34. And 2 times 17 will give us 34. So 2 times 17 gives us 34. And we're balanced. Okay. So let's get into the backyard and grill up some propane. And we are working outside. So we have plenty of oxygen. And so in our propane, we'll have carbon dioxide, and water is our example here. So 3 and 4 for our carbon and hydrogen. 3 times 2 is 6, right? And 4 makes 10. Woohoo! Okay, so we have an even number. So 2 will go into 10 5 times. So we don't have to do the fraction on this one because we had 10 oxygen atoms on our product side. 3 times 2 is 6 plus 4 will give you 10. So now we're balanced. Don't have to multiply through by 2 or anything. We're done. Yay, yay. Okay, let's see if the limited one works out that well. So carbon monoxide and water. 3 and 4 again. But now we have 7, and that 7 is problematic because 2 will not go into 7. And so now we have to do the fraction thing, 7 over 2. So we got 2. So funky looking 7, 7, 6, and 8. So we're balanced there. Okay, we've got one more to do here. This one, instead of octane, it's heptane. remember our prefixes from our covalent compound names. So we have C is excess, so it's CO2 plus H2O. Excess is always CO2 plus H2O. Limited is always CO plus H2O. Balance carbon and hydrogen first. 7 and 8 there. So now we have 14 and 8. 7 times 2 is 14 and 8. And I believe we'll get a number that's divisible by 2. 8, 9, 10, 11, 12, right? So it's 22. 2 times 11 will give us 22, and we're balanced. So that one's pretty easy. One more. So C9H20 excess. So we've got CO2 plus H2O here. We'll write it above my picture. So we got 9 here and 10 here. 10 times 2 is 20. So 9 times 2 is 18, and 10 times 2 is 9 times 2 is 18, and 10 will give us 28. And this one's a nice one also. It divides out quite nicely. It would be 14. 14 times 2 is 28. 9 times 2 is 18, and 10 makes 28 again. So now we're balanced. So in the next slides, we will be doing something that's a little bit more complicated. It's called net ionic equations, and we'll use some of the skills that we learned here to do those. I will tell you that in some high school chemistry classes, especially the first one, they may or may not do net ionic equations. So if your instructor does not require you to learn how to do those, you can skip the following slides. But if you're going on to college chemistry, it's probably a good idea to learn it as well. So we will catch those on the next slide. Okay, well, first we're going to talk about energy relationships in chemical reactions. And so let's talk about those. And we'll do an example as well. So it says breaking bonds is endothermic process. Bonds forming is exothermic. If the overall process determines the overall exchange. All right, so let's do an example of this. Let's use an acid-base reaction. Let's use hydrochloric acid plus sodium hydroxide. And the products here will be sodium chloride plus HOH or water, right? So when we break these bonds so that we can have new products, this is an endothermic process, okay? And when these bonds form, that is exothermic. So bonds breaking and bonds form. So if the endothermic reaction is greater than the exothermic, this would be an endothermic reaction. But if it goes back the other way, if the exothermic part is larger, then we have an exothermic reaction. And in fact, this one is an exothermic reaction because it is a reaction that forms an ionic compound. And so that is the general idea between the energy exchanges in chemical reactions. A lot of times you'll see delta H values, which is a fancy term called enthalpy, which means that the reaction occurs during constant pressure. Talk more about that in, I think it's unit 10, and delta H is negative here. So that's a little preview of our thermochemistry part. And so the main thing to remember is in this one is endothermic is when bonds break, exothermic is when they reform. If the exothermic part is greater than the endothermic, the whole thing's exothermic. If the energy required to break the bonds is more than what is formed, or released after the bonds come together, then it's endothermic. All right, now on to net ionic equations. I was so excited about net ionic equations, I couldn't hardly contain myself. Okay, net ionic equations. Okay, so let's talk about these net ionic equations. And we'll go over the steps, and we'll talk a little bit about solubility rules, and then do an example in this slide, and in the next slide we'll do several more examples. All right, so the steps are: write the balanced molecular equation. So that's just like we did in the previous slide with double replacement reactions. You put the charges above the symbols, you pair things of opposite charge on the product side. You charge balance those products by crisscrossing the charges to make sure this charge balanced. And then you balance the equation just like we did before. And then what you'll determine is what species will split, which will dissociate in the solution, and write them in ionic form. And then you cross out any duplicates, and then you write the net ionic equation. And in general here, rules, strong electrolytes will dissociate, and weak electrolytes and non-electrolytes will not dissociate. So thinking back to the previous unit, salts are strong electrolytes. They will split apart. Weak electrolytes are things like weak bases and weak acids. They will not dissociate. Insoluble substances and gases stay together. Strong acids are strong electrolytes and will dissociate, and weak acids are weak electrolytes. So those are some general kind of guidelines and trends. The solubility rules give you a roadmap to all that. And you still have to keep in mind the thing about the weak electrolytes and weak acids. And so you really need to know the strong acids here, and everything else will be a weak acid. And I'll give you a list of strong acids to memorize, and then you can consider all the other acids to be weak. And so these are a hierarchy. And so as you're looking at things, start at the top of the solubility rules. Start at this top here and work your way down. And if you do them in hierarchical form, you will come up with the right answers. So the ones on top of the ones on the bottom trump them, like group 1. All group 1 things split or dissociate into ions, even if they have something in them that might normally stick together. So as you're working through these, work through the list from top to bottom. And so let's work this first one out and come up with the net ionic equation, and then we'll go through and work several on the next slides as well. I'm going to write it up here so we'll have a little bit more room. We have silver nitrate in the aqueous form, and we have barium chloride, AQ. Okay. All right, so we're going to write the charges: +1, -1, +2, -1. All right, so now we're going to pair things of opposite charge. So we have silver and chlorine together, and barium and nitrate together. Barium's +2, nitrate's -1, silver's +1, and chlorine's -1. So we crisscross the charge there, and now we have a charge balance barium nitrate. And so this is one of the things I did when I was a student. I got excited and I started trying to figure out which ones would split and all sorts of things like that, which you have to do. But first you've got to balance the equation. So here we have 1 silver, 1 silver, 1 nitrate. We have 2 over there, so we have to put a 2 in front of silver nitrate. 1 barium, 2 chlorine, so we have to put a 2 in front of silver chloride. All right, so now we can start looking at our solubility rules and seeing what will split and which will not. Okay, So I'm going to look at silver nitrate first. And I'm going to look for nitrates, right? That's the second thing that I see here that kind of applies. The first one doesn't really apply. Nitrates, it says split apart, except for ethanonates and silver compounds. All right, so this first one's a silver nitrate. So it's one of the exceptions in the nitrate, so it stays together. So we'll just write it as a joined compound. Okay. All right, so now the next one is barium chloride. This is chlorides, bromides, iodides, except for silver, lead, copper, and mercury split. So it's not one of the exceptions, it's barium, right? And so now we'll write that as ions. It will split apart, okay? So the next one's another chloride, but it is a silver chloride. So silver chlorides stick together. So we have 2AgCl. And then we have barium nitrate. So all nitrates split, right? Nitrates here. All nitrates split apart, and it's not one of the exceptions. So this one will be written as ions, Ba plus 2 nitrates here. All right, so now we have an ionic equation, but it's not the net ionic equation. And the thing that we need to do is look for spectator ions. So here, spectator ions are things that are exactly alike on the reactant and product side. And so we have silver nitrate. We don't have silver nitrate over here. We have barium plus 2, and we have barium plus 2 here. So barium is a spectator ion. It doesn't really enter into a chemical compound. It's just an ion in solution. So we cross it out. And we have 2 chlorines, but we don't have 2 chlorines over here. So barium's the only spectator ion. So let's write the net ionic equation minus the spectator ion. We have silver nitrate plus chlorine gives us silver chloride plus nitrate. Okay, so you notice here that we have coefficients of 2, 2, 2, and 2, which is the same as 1, 1, 1, and 1. So we can take our eraser here and we can erase these coefficients. I can grab an eraser. So that will be our final net ionic equation. And you should always go through and make sure that your net ionic equation balances as well. So we'll do some more examples in the following slides. Okay, so now we're going to do some more examples of net ionic equations. And to save us a little bit of time, I wrote the balanced products to get us started. So we can start with the second step, determining which one of the species will split or which ones will stay together. So let's take a look here. We've got sodium carbonate. So that is a group 1 metal. So that will disassociate. Remember, these are hierarchical, which means you'll start at the top and go to the bottom. And then we have sulfuric acid, which is one of our strong acids, so it will disassociate. Again, a group 1 or an alkali metal will disassociate, so we have 2 sodium ions here, so sodium sulfate will disassociate. And then we have carbonic acid. And carbonic acid is a weak acid, so normally you would think that that would stay together, but it is one of those kind of exceptions that you have to have memorized. Carbonic acid is responsible for carbonating beverages, and so it always splits into CO2, carbon dioxide plus water. And that's way cool, right? And so now we have to figure out what our spectator ions are in this equation. So we have sodium on both sides, Na. Carbonate we don't have on both sides. We have carbon dioxide, so that doesn't match, so we can't cross that one out. We have hydrogen ions on the reactant side, but no hydrogen ions on the product side. We have sulfate ions on the reactant side and sulfate ions on the product side. So we have two spectator ions, sodium and sulfate. And so now we've got to write our net ionic CO3 plus 2 hydrogens gives us carbon dioxide and water. Oh, CO2 plus H2O. All right. So that balances out 1 carbon, 3 oxygen atoms, because we got oxygen and carbon dioxide and oxygen and water, and 2 hydrogen ions. All right, so let's move on to the next one. This one is sulfuric acid and barium hydroxide. Strong acids will dissociate. Usually, carbon or hydroxides do not dissociate, but barium is one of the exceptions. It dissociates. So we've got barium here plus hydroxides, 2 hydroxides there. Sulfates do not dissociate. Let's see, double check barium sulfate here on my chart. So sulfates are usually slightly soluble, but barium is an exception. It is insoluble. So here we have barium sulfate sticking together, and then water will stick together as well. So this one doesn't have any spectator ions. So on this one, we just we write the ionic equation and the net ionic equation are the same things. So we're good there. All right, our next one is acetic acid plus sodium hydroxide. Acetic acid is a weak acid and it does not dissociate to any extent. And then sodium hydroxide, group 1, right? They always dissociate. Sodium's in group 1. And then we've got our yield sign here. And we got sodium acetate. Well, that is a group 1, so it will dissociate. And then we have our water molecule that stays together, of course. All right, so let's look at this and see if we can find our spectator ion or ions. Sodium is the only one that I see. Let's double check. Okay, that is it. So our net ionic would be acetic acid here plus hydroxide yields acetic acid or acetate ion, sorry, plus water. Okay, very good. Now, I have a lot of practice problems in the practice set, but to really get good at this, you got to do lots and lots of practice. So there is a website called ChemTeam, and if you type in ChemTeam in a search bar, you can find yourself some more practice problems in addition to the ones that I gave you. So if your instructor is having you work on these, do as many practice problems as possible. One of the general solubility rules is if things with large charges tend to stick together, like +3, -3, -2, +2, they tend to stick together. Things with lower charges like +1 and -1 tend to split. Of course, there's lots of exceptions, and we've done some exceptions in the example problems here. But as you're going through, look for the general trends and memorize the exceptions. So very good. I hope you've enjoyed the recordings on chemical reactions. And in the next unit, chemical quantities, we'll be reviewing the chemical reaction part as well, because to do the chemical quantities, you need to be able to predict products and balance equations as well. So I'm looking forward to Unit 7. This is the end of Unit 6, and looking forward to see you on the flip side.